Am I audible to you guys? Sorry, I cannot hear you. Now my screen is visible. Is my screen visible?
Yes, it is.
Okay then. Fine. Let me then switch to my presentation. So, okay. So today's session, it is the second week of the tutorial for the course Technologies for Clean and Renewable Energy Production. So the various topics we will be discussing in detail today are various different routes for production of energy from coal apart from combustion, which is the conventional conventional method for the energy production. So we will be studying about these are the various techniques such as oxy-fuel combustion, chemical looping combustion, gasification, direct liquefaction, underground coal gasification, and we will be studying about gasification and direct liquefaction in detail. So let me and some of the topics related to syngas conditioning, how syngas can be used for the further downstream applications such as for the synthesis or production of various chemicals and in production of power and electricity. So all these we'll be studying today. So coming on to the first slide, it is telling about the pre-treatment of coal. Basically what happens, I told you in the last class as well, there are two techniques for the uh, either we can modify the conventional techniques or we can introduce some new techniques. So the modification in the conventional techniques would be if we do the pre-treatment of our of our coal, of our crude coal material, uh, or the newer techniques such as oxy-fuel combustion and gasification, liquefaction, etc. So firstly, we will be talking about the modification, some of the pre-treatment that can be done to the coal so that lesser emission of carbon takes place in the environment. So basically, coal consists of various elements such as carbon, hydrogen, oxygen, sulfur, nitrogen. So the most so the sulfur is one of the element which is not required, which is actually undesirable. So sulfur in coal is present in mainly in different forms, in organic forms such as pyrite. Just a second. In organic forms such as pyrites, then sphalerite, galena, then marcasite. As so all these forms, they can be removed, they need to be removed actually from the coal for to decrease the various emission gases from the while combustion. So there are three ways it can be reduced, in a physical method, in chemical method, or biological method. So physical method includes jigging, tabling, dense medium processing, hydrocyclonic, and air classification. So jigging basically it deals with the difference in the acceleration. So when suppose a sample is falling from a height, so difference in the acceleration of different particles depending on its mass, they separate. So that is jigging. Dense medium processing is if we form a slurry of the coal sample, then the different medium, or depending on their density, separate out. Hydrocycloning is mixing the coal sample with that water, and if we rotate them in a kind of in a centrifuge, then the components separate out depending on their density. Chemical techniques involves oxy desulfurization and dehydroxy hydrodesulfurization and caustic treatment as well. As we know that the sulfur, it is acidic in nature, so if we use some alkaline medium such as NaOH, so it can neutralize and we can separate out the sulfur. And biological desulfurization, and it is done using various bacterial cultures. Coming on to two different, for all these techniques, mostly two different types of reactors are used. The first one is fixed bed reactor and the other is fluidized bed reactor. So the difference between them I will show you here. Okay, just a second. So in fixed bed, what happens is all these mean the catalyst or the coal sample which we are using, it is in a fixed state. But in fluidized bed, the particles are very fine in size, mean the smaller is smaller in comparison to the fixed bed reactor. So what is the difference? In fixed bed, the contact between the gas, that is the steam and oxygen that we are given, the contact between the coal sample and the gas is not that good because of the packed structure. But in case of fluidized bed, what happen is when we provide the oxygen from below, due to very finer particle size, all they form they suspend in they form a suspended formation, and due to the uniform suspension, the contact between the gas and the coal sample and the finer the particles of coal is very good, and heat transfer coefficient is also very good. That's why here combustion is better than the fixed bed reactor. So this is a, just a second. So this is a fluidized bed reactor flow chart, which shows that from here we give the coal sample and limestone. The one another advantage of just a second, if someone is trying, just a minute, is anyone trying to admit? Okay. Okay. So in this, from here we take the coal sample and here limestone is taken. What is the purpose of limestone here is the removal of sulfur present in the coal sample, and here fluidized bed forms when we from here gas comes, and due to the formation of fluidized bed, and after the combustion, some particles also go into the regenerator. So there is enrichment of CO2 taking place. So the only problem with this fluidized bed, there is also a problem. The only problem is that the here very finer particles are required. So to crush the coal sample into very finer particles, some extra energy is required. So that is the only disadvantage of fluidized bed reactor. Just a second, someone is trying to add, I guess. Coming on to in the last class also I told that till now various boilers for heat recovery are operated in subcritical condition, but if we try to operate them in supercritical, advanced critical and ultracritical condition, then the emission decreases. So here are various conditions for the subcritical. We can see that it is done at lower temperature and pressure, whereas the supercritical is done at higher temperature and pressure than the supercritical. And we can see here that due to the change in this, the efficiency is increased from 35 to 37. Moreover, again, if we increase the temperature and pressure in advanced critical, the efficiency again increases, and likewise in the ultra supercritical also. So we can see here the trend that if we increase the pressure and temperature, then the net energy efficiency also increases. But this is actually till now not practiced. For now, only subcritical condition is practiced in various industries. So we are currently in the state of switching from subcritical to supercritical. Now coming on to flue gas desulfurization. This is a flowchart for the removal of sulfur from flue gas. So as we can see from here, flue gas goes in, and here limestone slurry is also introduced, which is introduced from here, and it is also regenerated. The limestone is also regenerated from the same procedure. What happens is, after the usage of limestone in this reactor, it goes to the thickener where this limestone slurry thickens up, it gets concentrated, and this for again using it as gypsum, and the water which is present is taken in by the taken as makeup water for the for using the limestone slurry here again. So basic, just a second. So here flue gas and limestone here, from here limestone is sprayed, and from here flue gas is taken, which is in this area it gets in contact, and elimination of sulfur takes place. Another technique, which is oxy-fuel combustion. So in conventional combustion, what happens is we do the combustion. The combustion is done in presence of excess air, which consists of all the components present in air, such as oxygen and nitrogen. But in oxy-fuel combustion, what we do is the combustion is done purely in the presence of oxygen. So therefore there is no presence of nitrogen and sulfur. So what happens is, air separation takes place. We separate out nitrogen, and this air is introduced into the boiler where the fuel is introduced, and here combustion takes place, and then here in the condenser heat recovery is done, and again the CO2 which we gets here, it is again recycled back to the boiler for enrichment. So we get a much better larger CO2 recovery, that is almost 90% CO2 recovery is done in this procedure. Coming on to one of another technique, that is chemical looping combustion. So it is basically this combustion takes place in the presence of some chemical. As the name itself tells, the combustion takes place in the presence of some chemical. So what happens is, we take a metal which is oxidized using air to metal oxide, and this metal oxide further assist in the combustion of the of our coal sample. Then again further this metal oxide is reduced to metal to use it in the another cycle, mean to for the combustion of another sample of coal. So basically here we can see, this is the reaction for the oxidation of metals, and this is the metal oxide which we get here during the oxidation. This metal oxide, when in reaction with the carbon present into the coal sample, it gives CO2, and it is also in turn reduced to metal again. And this metal also, this metal oxide on reaction with hydrogen present into the in our sample gives H2O. So this is our requirement, CO2 and H2O. So seeing this flowchart, it gives us the efficiency of this procedure. What happens is this: the reaction of oxidation of metal from metal oxide is exothermic in nature. So it gives this heat, Q hot, and the reaction of this metal oxide with fuel, which gives us CO2 and H2O, is endothermic in nature. So it takes this Q cold energy, and this is the heat given out by the procedure, and this is the work done. So doing the balance here, we can say that Q hot equals to Q cold plus Q naught plus Q what that is W work done, and Q naught is T delta is that is a change in entropy. So coming on to gasification, gasification is basically the conversion of this coal sample into various gases. So what happens is there is one important factor which plays an important role, a crucial role while gasification, that is oxygen to coal ratio. Basically, we use oxygen for the combustion of coal samples, so oxygen to coal ratio plays a very important role. If this oxygen to coal ratio, that is R, is greater than 2.5, that then what happens is that this is the conventional route. Simple combustion is taking place. So it gives oxygen, water, and carbon dioxide. But if we reduce this R ratio less than, just a second, what happened? So if we reduce this R ratio less than 2.5, uh, in between 0.68 to 2.5, then we get is then the procedure that takes place is gasification. In this, what we get is the syngas. The concentration of CO and H2 is higher. H2O and CO2 is also present, but their amount is less than CO, carbon monoxide, and H2, which is collectively called syngas. And if we further reduce this ratio to less than 0.68, then pyrolysis takes place, yes, and we get carbon and syngas. Another one of the technique is direct liquefaction, in which we do is the conversion of this solid coal sample directly into liquid fuels which can be used in various transportation. So which we will be discussing in detail further. One another technique is underground coal gasification. What happens in this is we don't require any external reactors or anything. What we do is we introduce air or oxygen and steam into the underground coal seam, I mean where coal is present. Just a second. And we introduce this air, oxygen, and steam here, and ash formation takes place, and moreover syngas formation takes place, which goes up through this, and we can get various gases such as CO2, carbon monoxide and hydrogen, methane, steam, etc. The advantage of this is, as I told, no reactor is required, dust and noise is less because it is taking place underground, and ash is also collected below. Ash handling is not required, mean external procedures for ash handling is not required. No coal stocking and transportation, there is no such problem related to transportation. Larger coal resource exploitation, we can exploit the coal resources on a larger scale. Convert sulfur, we get here convert sulfur to H2S and nitrogen to NH3 E instead of instead of sulfur dioxide and nitrogen dioxide, which are more dangerous in, more poisonous in nature. But the only disadvantage with them is that it may cause aquifer contamination, that is groundwater contamination. It can cause surface subsidence can also occur sometimes if there is some hollow. Due to this procedure, if hollow occurs inside the ground, then surface can collapse. And another problem is expensive drilling, and the machinery required for all this procedure and drilling, etc., is quite expensive. Coming on to one of the techniques which we'll be talking in detail, that is gasification. It is the process that converts carbonaceous feedstock, that is our coal sample. It converts this coal sample into combustible gases such as hydrogen, carbon monoxide, carbon dioxide, and methane with specific heating value in the presence of partial oxygen. Basically, it is done in the presence of controlled oxygen. The produced gas is air. Here it is called syngas. Basically, what we get is carbon monoxide and hydrogen in large quantity, in large percentage. So that is collectively called syngas. And this syngas can be further used for the production of various liquid fuels used through indirect method through Fischer-Tropsch synthesis. And if in place of oxygen we use air, then it consists of nitrogen also. Then here the produced gas, carbon dioxide and hydrogen, also contain nitrogen, high amount of nitrogen. Therefore, it is, and this gas is called producer gas. Just a second. Okay, then these are some of the basic. This is the basic chemistry which is required, which is involved in coal gasification. The first one is we are mainly talking about the carbonaceous material. So we will be the coal sample, while gasification consists of what we take is coal and the oxygen and steam. So we will be basically focusing on what reactions will be taking with the carbon. So when gasification with oxygen, carbon reacting with the limited amount of oxygen gives carbon monoxide. It is a exothermic reaction, and combustion with oxygen means excess oxygen, it forms carbon dioxide. So these both are exothermic reaction. So what happens is initially we are giving energy, and these two reactions which are exothermic in nature will further give energy for the other side reactions which are not in large content. So gasification with carbon dioxide, if carbon with again reacting with carbon dioxide, it gives carbon monoxide. Then carbon on reaction with steam, that is H2O, it gives syngas, that is carbon monoxide plus hydrogen. Then gasification with hydrogen, reaction of carbon with hydrogen gives methane gas, and water shift reaction also takes place in these. Just a second. These two reactions are endothermic. Further, these three reactions are again exothermic. And water shift reaction takes place, which is carbon monoxide plus water. Because carbon monoxide we cannot release it in the environment. This is a poisonous gas. So we, on reaction of this carbon monoxide with hydrogen with water, we get hydrogen, which is also a very good energy source. And methanation reaction takes place, which is carbon monoxide plus hydrogen, which gives methane. So coming on to the comparison of two basic products which we get while the combustion, that is the one is syngas, that is carbon monoxide plus hydrogen, and the other is producer gas, which is formed when we use air instead of oxygen. So there is increase in the nitrogen content. As we can see, hydrogen content, the syngas content, that carbon monoxide and hydrogen content of syngas is more compared to producer gas, that is 20 to 30, where it is less, that is 13 to 90%, and carbon monoxide it is 40 to 60%, and here it is 18 to 22%. And the carbon dioxide content also it is less, that is from 5 to 15%, it is here 9 to 12%. But the thing to focus here is that the amount of nitrogen here in syngas it is 0.5 to 4%, whereas in producer gas it has increased a lot, that is 45 to 55%, which is the proof that air is used here instead of oxygen. So as we know, air consists a large amount of nitrogen. So this is the basic difference of syngas and producer gas. Moreover, its heating value is also, producer gas is not that desirable. Its heating value is also less compared to syngas. Coming on to the steps involved in gasification, what happens is we introduce the feed from top and steam and oxygen from below, what happens is here it is a greater. So oxidation takes place from at the lower zone, then the reduction, then pyrolysis. As we go up, the oxygen content starts to decrease. So as we know that pyrolysis takes place in the absence of oxygen or in the least amount of oxygen. So as we go up, oxygen amount is decreasing and pyrolysis takes place here, and in the upper zone only drying takes place, that is the drying of volatiles and moisture content, if any present, that takes place here. So here we can see that the oxidation takes place, the steam is introduced from below. So the temperature is highest in this zone and it starts to decrease and is the lowest in this zone where gas comes out, the effluent gas, that is flue gas, comes out. So these are the process which I explained here: drying, pyrolysis, reduction, oxidation, and ash cooling. Ash cooling, let me tell you what happens is after the combustion, ash gets accumulated on this crater or it gets sieved out from below. Coming on to syngas production and efficiency. So what happens is the syngas production is given by this formula. Fuel gas production, that is basically fuel gas we are talking about, is syngas. What we have done is the nitrogen balance. So here it is the airflow rate into 0.09 into 0.79. So this 0.79 we have taken that in air we have considered that it is 79. Sorry, just a second. As we know, we have considered that air consists of 79% of nitrogen. So here we have taken the airflow rate, that is the amount of nitrogen in the air, which is shown by airflow rate into 0.79, and this is here 100 minus carbon monoxide plus content of carbon dioxide, content of hydrogen, content of methane, and content of C2H2, which is showing us that we have excluded the considering air as 100, so we are excluding all other components which do not contain nitrogen. So we are so this is also the amount of nitrogen present into feeding rate. So this is the nitrogen we have fed and this is the nitrogen which we have got in our feed, so in our effluent. Moreover, the yield of hydrogen and carbon monoxide can be calculated by the hydrogen atoms which are present in the syngas, that is the amount of hydrogen atoms which we get in the syngas and the amount of hydrogen we are injecting that is uh, uh, we are injecting in the form of steam, or the other reactant is oxygen, so there is no question of hydrogen there. And for carbon monoxide is also same, the carbon atoms in formed carbon monoxide, that is in the syngas, indirectly it is written that, and the C atoms injected, that is the carbon present in the coal sample. And this is the efficiency, syngas efficiency, which is given by a lower heating value of cold gas, that is the syngas, into the fuel gas production upon lower heating value of coal treated plus allowed thermal power upon coal flow rate. Coming on to some of the factors influencing gasification, there are various factors which influence the gasification. Mainly they are the type of feed injection. So if the type of feed injection, meaning if the coal is induced from the top or from the side, that also affects the gasification. The gasification agent used, if we are using solely oxygen or air, as I told that in presence of oxygen we get syngas and in presence of air we get producer gas. So that also affects the gasification. And the type of heating, it can be done either by partial combustion, if we are doing partial combustion, or external source, heat is provided from external source. All these things also affect the gasification. And the temperature and pressure range in which we are operating the gasifier is also a crucial factor. Coming on to flow sheet and utilization scheme of gasification. So flow sheets clearly shows that coal is induced into the gasifier here, the pre-treated coal, and the oxygen and steam is induced from below, and this gasification takes place in raw syngas first. it is the cleanup of the syngas is done in two stages. The cleanup of syngas we will be studying in our further slides. I'll be telling them in detail. And the cleaning residue, the residue from this cleanup is again refluxed back into the gasifier for further treatment. In the second stage cleanup, we are cleaning up the various if some kind of acid is present, and then after the cleanup, this syngas is taken for downstream applications. As I told that syngas can be used for the production of liquid fuels, or again it can this syngas consists of carbon monoxide and hydrogen, so hydrogen separation can be done, and this hydrogen can be used for hydrogen vehicle fuel and in fuel cell for the production of electric power. And then this hydrogen gas can further be sent to gas turbine for electric power, and waste heat boiler for heat recovery, which will yield the flue gas, and the steam turbine for production of electric power. So this scheme clearly tells us that the syngas can be used for various downstream applications, and further after the heat recovery here, this steam is sent back to the gasifier as it is one of the reactant for gasification. And from below we get the ash and slag material if some after the combustion. So coming on to some major kinds of gasifiers which are used for coal and pet coke, there are basically three types and one is the modified one. Three types, the first one is moving bed. We induce the coal from top and the steam and oxygen from below, and ash is collected below. So here what happens is this is the moving bed, and as we move as we here combustion takes place. Here the temperature is low, but here where in the middle combustion takes place, so the temperature profile clearly shows that firstly the temperature increases, it reaches to a maximum here, and then starts to decrease, which is the temperature starts to decrease in this zone. The second one is fluidized bed reactor. This is one of the most efficient reactor. What happens is we induce the steam and oxygen from below and coal sample from side, and due to the fluidization there is more contact of steam and oxygen with coal, and combustion takes place here. So in this it is shown that the temperature starts to decrease. In this zone it stays constant due to the uniform dispersion, uniform suspension type arrangement of fluidized bed. It stays constant here and starts to decrease in this zone. And the third one is entrained bed. In this, the coal and steam and oxygen are both introduced from the top. So the coal and the steam and oxygen are moving both in the same direction. So here the highest temperature is in this zone and starts to decrease here. So we can see that the temperature starts to decrease, it is constant, and due to this lower going arrangement, the temperature is stays constant at the highest for a long time. So these two are the one of the two these two are the efficient type of gasifiers. So to introduce the qualities of both these reactors, both these gasifiers, another type of, that is, transport reactor gasifier was introduced. In this here steam, oxygen and fuel is introduced here. Some sorbent is also, some kind of adsorbent is also used here, which absorbs the sulfur if some sulfur is present. So here fluidized bed formation takes place, and it rises from here and goes into this from here, both as due to the flow rate of the oxygen and steam, this oxygen steam along with coal sample goes up in the riser, and from here falls down below in the form of entrained bed. So this is the entrained bed arrangement, and from here if some kind of regeneration of the coal sample can also take place, that involve that in turn enriches the carbon dioxide formation and the syngas formation. So this is the arrangement involving both fluidized bed as well as entrained bed. Another type of gasification is the plasma gasification. What happens in plasma gasification is the high voltage is applied across two electrodes, which accelerates the free electrons, and these electrons collide and ionize and form a streamer, an avalanche kind of electron streamer, which further these electron stream helps in the oxidation of our combustion of our coal samples. So torch power levels from in the plasma gasification is from 100 kilowatt to 200 megawatt, produces energy density of up to 100 megawatt per millimeter cube. And the high energy electrons can work on all type of molecules, and they create radicals and helps in the combustion of carbonaceous materials for the production of carbon monoxide and hydrogen. Now let us come to another section, that is the cleanup of syngas. So the syngas that we get during the combustion of coal sample, it needs to be cleaned up. Various techniques are introduced. So we will be talking about the various methods for the cleanup and cooling of our syngas. So coming on to first, that is the two modes of operations for gasifiers. For the cooling of syngas, two modes are used. The first one is quench mode and the second one is boiler mode. So in this one is the quench mode. What happens is we introduce the oxygen and steam from here and the coal also from the upper side, and syngas formation takes place. So this syngas here is quenched by water, that is quenched by water shock, that is it is instantly cooled, and it at the bottom of the separator suits, and in the bottom ash gets settled. So the steam here produced is of lower temperature as compared to the one produced in boiler mode, and and it produces a 1.47 to 2.94 millipascal pressure of steam. The second method is of boiler mode, which the feed is introduced from here and steam and oxygen is introduced from below, and syngas formation takes place here, and further this syngas is sent to a boiler for or heat recovery, and here you can see that it produces a high pressure steam of 9.81 to 13.73 megapascal of pressure of steam. Further coming to the separation of particulate matters, as we know the syngas also consists of some particulate matters. So for the removal of particulate matters, different arrangements are made. So first one is spray scrubber. What we do is the dry gas is introduced from below, the syngas is introduced from below, and water is sprayed from above, and with this spray this water takes away all the particulate matters which settles down below, and the clean gas comes out from the top side, and it gives a very good efficiency of about 94% for 5 micrometer particle and 99% for 25 micrometer particles. Another type is the packed bed and plate column scrubber. In the similar water scrubber, we have introduced some kind of packed bed here. So dirty gas is introduced from below and the clean gas goes from top, and the liquid is sprayed here. So due to the presence of these plates, there is more contact between the dirty gas and water, and particulate settling takes place. This packed bed gives more residence time for the settlement of the particulate matters. One another arrangement is plate column. Instead of this packed bed, we have introduced the plate column. So the liquid which is sprayed from above, it gets settled on this, and while overflowing comes onto this plate, on overflowing comes onto this plate, and likewise it also cleans up, scrubs away all the particulate matters present in the syngas. And the packing materials may include different kind of materials such as rashing rings, saddles, coke and broken stone, etc. Coming on to syngas cooling and conditioning, this method is along with the syngas, if some kind of acid components are present, so for the removal of those acid gases, this arrangement is done. So what we do is the raw syngas is given here. Here COS hydrolysis takes place. If there is COS traces are present, which may convert into carbonic acid and sulfuric acid. So this COS hydrolysis takes place here, giving carbon dioxide and uh, hydrogen sulfide, and this carbon dioxide is for the acid gas removal is taken up here for carbon dioxide gas enrichment, and carbon sequestration can take place after compression. And the H2S is taken here, which is for H2S gas enrichment, and sulfur recovery is done here, and further after this acid gas removal we get our clean syngas. Another method for acid gas removal involves the solvent absorption and adsorption procedure. So in this what we do is we introduce some kind of solvents into our along with into our syngas. We take the dirty syngas from here, and some solvents are introduced from the upper side. So on contact with these solvents, various acid gases are absorbed and removed. So by introducing MDA, it is a chemical, some of the solvents involved are MDA, Selexol, Rectisol, which involves the absorption of various acid gases present in the syngas. Another technique, these were the absorption based techniques, and one of the technique is adsorption based, that is warm syngas cleanup, which is a new technology. So warm some of another technique for the removal of acid gases is water gas shift reaction. So basically it is carbon monoxide present cannot be directly effluated into the atmosphere as it is poisonous in nature. So we can extract hydrogen, which is a useful fuel. We can extract hydrogen by reacting of this carbon monoxide with water. We get hydrogen and carbon monoxide and carbon dioxide. So there are two types of shift reactions. That is based on temperature, it is high temperature shift reaction, and another is low temperature shift reaction. So these both reactions operate at different temperature. Not only temperature is different, along with that different catalyst is used in both these reactions. And another based on if the water gas reaction took place before acid gas separation or after acid gas separation. So if this water gas shift reaction took place before acid gas separation, then it is source shift reaction, and if it is taken place after acid gas separation, then it is sweet shift reaction. So here I told that two different types of catalysts are used in high temperature and low temperature shift reaction, but it is not mandatory. Similar catalysts can also be used, such as cobalt molybdenum or alumina. Cobalt molybdenum and alumina catalysts can be used in both these reactions. So syngas utilization, various applications of syngas includes it can give hydrogen for hydrogen fuel vehicle fuel. It can give electricity. It can be used for electricity production, for fuel liquid fuel synthesis such as naphtha, waxes, diesel, and for the formation of various for the synthesis of various chemicals such as methanol and its derivatives, such as given here dimethyl ether, ethylene propylene, polyolefin, etc. Now coming on to one of the other technique which we will be talking in detail, that is the direct liquefaction process. So what is direct liquefaction? It is basically the conversion of our coal sample into liquid fuels. So as we can see here, this is the coal sample. This is the coal sample. Hydrogenation is done. What we do is, as we know, let me tell you, just a second. As in the last class, in the initial classes, it was told that the structure of coal involves various aromatic rings. It is a very complex structure. So what we do, if we break these aromatic structures and introduce some hydrogen along with it, what we will get is the lower molecular weight fuel, which will be liquid in state. So we are trying to extract the liquid lower molecular weight liquid fuel, which can be further used as transportation fuel in in various vehicles. So uh, one other thing is that as we saw that the heating value of the high rank coal, that is uh, anthracite, is good, but here what we have seen that during the production of liquid fuel from coal, as low as the rank of coal, the better the quality of the liquid fuel such as gas oil, gasoline and kerosene will be there. So here we are using basically low rank coal, that is lignite, subbituminous and bituminous. We will be doing the hydrogenation at high temperature and pressure of coal, and after distillation we will be getting gas oil, gasoline and kerosene. So this is the scheme for direct liquefaction. We take coal, we do the fragmentation. We have to reduce them in size, so crushing and all is done. Along with that, uh, some solvent is used for dissolution. Basically, we have to prepare a coal slurry. So large amount of solvent is required. Then the hydrogen is introduced for hydrocracking and hydrotreating at high temperature and high pressure. And if some kind of catalyst is required, it is not mandatory. Catalyst either is required or it is not required. And after that, what happens is we get one liquid part, that is oils, and one is the solid part, that is free asphaltenes and asphaltenes, which further on catalytic hydrocracking, by introducing hydrogen, we get the most we can get the oil from this solid part as well, which on hydrotreating can be used as transportation fuel, and this solid part is further and it gives the higher molecular weight asphaltenes. So different types of direct coal liquefaction includes various techniques. The two main techniques are the single stage direct coal liquefaction, and the second one is double stage direct liquefaction. So single stage, basically it gives distillate in one primary reactor, only one reactor is involved, and in this two reactors are involved. So basically the hydrogenation is taking place in two steps. So the first one is SRC2 and Exxon donor. They both are quite similar to each other, but this one is taking place at a lower lower temperature, and this one is taking place at a bit almost equal or bit higher temperature than this, but the pressure is more here. And in H coal, here no catalyst is used in these both reactions, but in this reaction, H coal reaction, catalyst is used. Whereas in the two step, the first one here, it is a two-step coal liquefaction process, and it is a multi-step liquefaction process. Here various catalysts are used, but here it may be a catalyst may be used or may not be used. So let us come to some of the questions that we will be discussing in this class. Just a second. Am I audible to all of you? Are you guys listening? Someone is trying to join. What? Am I audible? Hello? Okay. So let us start with the assignment part of the session. I want you guys to answer, okay? So coming on to the first question, which is which of the following is a physical method for separation of sulfur from coal? Anyone from the student side? Hello? I want you guys to answer. So no one knows the answer? It is hydrocycloning. Okay, let's come to the second question. that is, calculate the amount of work done in the burning of carbon in a nickel-based chemical loop combustion process when the change in entropy delta S naught is 350 joule per Kelvin and the working temperature is 310 Kelvin. These are the two reactions. So, can someone tell me how to do it? Does anyone have idea? I want you guys to try the question and then I will tell you what will be the solution. So this question is basically based, hello, okay, then let me come to the question. This question is based on chemical looping. So what is happening here, it is given that two reactions are taking place. Okay, this reaction, this is the oxidation of metal. From that oxidation of nickel to nickel oxide is taking place, which is the reaction of this is the oxidation reaction. So this is Q hot given here, 396 kilojoule, and this is the reduction of nickel oxide to nickel, which gives, which is a endothermic reaction giving us Q cold, that is 136 kilojoule. And heat given out, that is Q naught, is given by T delta S naught. So T and delta S naught is given in the question, that is 350, sorry, 310 into 350, which gives 151, sorry, just a second. It gives 108.5 kilojoule of energy of heat is given out. Now coming on to the formula in the question, as we saw, it is Q hot equal to Q cold plus Q naught plus W, that is work done, which is required here. So it will be 396 minus 136 minus 108.5, which will give us the answer, that is 151.5 kilojoule or 151,500 joule. So this is the answer here. The B1 is the answer. Any confusions? Okay, let's come to the next question. I want you guys to actively participate in this assignment. So, the third question is, Fischer-Tropsch synthesis is normally used to convert syngas into. Someone from the student side now answer the question. The answer to this is liquid fuels. In the gasification process, when air is used in place of oxygen, the produced gas contains a high amount of. Anyone? No one knows the answer? Okay, then let me tell the answer. It is nitrogen. So, as I told that if in place of oxygen we use air during the combustion, then the produced gas it consists of high amount of nitrogen. Coming on to the other fifth question, that is high temperature water gas shift reaction requires a temperature range of. Anyone? The answer is 320 to 450 degrees C. The sixth question is which of the following product is not normally obtained by the processing of syngas? The answer is coal. All other products are produced that after the synthesis we can get hydrogen also, electricity also, waxes also in the form of liquid fuels. But coal, which is the reactant for syngas, so we cannot get it back. Seventh question, which of the following is not a type of single stage direct coal liquefaction process? This I told just now. Anyone? You guys can answer. The answer is catalytic multi-stage liquefaction. The most favorable condition for the H-coal process is. It is 425 to 455 degrees C and 200 atmospheric pressure. Coming on to the ninth question, that is match the following process with their applied catalyst. So the answer to this is H-coal uses cobalt molybdenum on alumina catalyst and CTSL uses nickel molybdenum on alumina catalyst. Now coming on to one another numerical question. So I would like you guys I would like if you could answer. So try solving this. Just a second. Are you guys even trying the questions? Am I not audible to you guys? No one, none of you is unmuting your mic and giving answers today. Okay, then I will continue with the questions. You may see the solutions I am giving. That may help. Okay, then let me start with this question. A peat sample has the following composition on mass basis, that is carbon 40%, hydrogen 5%, oxygen 30%, nitrogen 0.40%, sulfur 0.10%, moisture 19.5% and ash 5%. Determine the heating value of the peat sample using the following relation on dry and ash free basis. The equation for higher heating value is given here, that is HHV in megajoule per kg, that is 0.3516 into carbon content plus 0.1.16225 into hydrogen content minus 0.1109 into oxygen content plus 0.0628 into nitrogen content plus 0.10465 into sulfur content. Okay, then let's start with this question. So, let us assume 100 gram of peat sample. Okay. So if we assume 100 gram of peat sample, then we can say that we have 40 gram carbon, 5 gram hydrogen, 30 gram oxygen and 0.40 gram nitrogen, 0.10 gram sulfur, 19.5 gram of moisture, that is H2O, and 5 gram ash. So we have to find the heating value excluding mean on relation with dry and ash free basis. So excluding moisture and ash. So let us see here: carbon, hydrogen, oxygen, nitrogen, sulfur. So it is 40 gram carbon, 5, 30, 0.40.1. So on dry and ash free basis, if we calculate for carbon, it will be 40 into 100 upon 100 minus 19.5 minus 5. So this value, it will be 75.5. So after calculating this, we will be getting 52.98. Likewise, so on dry and ash free basis, carbon content is 52.98%, hydrogen will be 6.62, oxygen will be 39.73, it will be 0.529 and it will be 0.132. We will not be calculating moisture and ash because it is asked for dry and ash free basis. Now we have got all the content of all the elemental content on dry and ash free basis. So after putting all this in equation given in the question, so after solving this equation, you will be getting the answer, that is 21.96 megajoule per kg. So the higher heating value on dry and ash-free basis is 21.96 megajoule per kg. Is this clear to you all? At least say yes or no. Am I audible? Okay, fine. If it is clear. Okay then. Let's go to the next question. So, which of these forms of sulfur is present in coal? The answer to this is all of these forms. As I told in the slides, it consists of FeS2 also, organic sulfur also, and various forms such as sphalerite, galena, and marcasite. Why fluidized bed reactor gives relatively higher efficiency? The answer to this is both A and B, since it provides more contact between coal particles and air, and second one also that recycling of unburned coal is possible, that is regeneration is possible. If some amount of coal is not still burnt into the reactor, then it goes into the regenerator, and then after recycling it comes back into the reactor again for further combustion. So it gives better efficiency compared to other reactors. So now coming on to the third question, which is in chemical loop combustion at what elevated temperature around disk to disk metals reacts with the oxygen in the air in an exothermic reaction producing metal oxides? The answer to this is 700 and around 700 to 900. The metal reacts with oxygen in the air for oxidation and converts to metal oxide, as it was given. Sorry. This equation, the oxidation of metal takes place from temperature 700 to 900. Net energy efficiency and higher heating value of ultra supercritical boiler are. The answer to this is 44% and 7757 BTU per kilowatt hour. Coming on to the other question, that is syngas can be used for various applications including liquid fuel, diesel and gasoline produced through. The answer is Fischer-Tropsch synthesis. Coming on to the sixth question, that is syngas conversion efficiency of thermal power plant is between dash percentage to dash and dash percentage for a single cycle steam power plant. The answer to this is 30 percentage and 40 percentage. The efficiency is between 30 and 40 percentage. The question 7, that is syngas conversion efficiency of a combined cycle gas turbine CCGD power plant may be. The answer to this is up to 60%. Eighth question, which is which statement is not true about advantage of gasification? The answer to this is none of these. All these statements above are advantages of gasification. It reduces carbon dioxide emission. Its accurate combustion control is there since it is done in controlled oxygen atmosphere. Then higher thermal efficiency is also there compared to conventional combustion, which is done in the presence of excess air. Coming on to which catalyst is used in CTSL process? The answer is nickel molybdenum or alumina. So this is a gasification flow sheet. Flow sheet is shown here. So identify the P and Q. Here P and Q. What would be P and Q? This is a steam turbine and this is a gas turbine. Since we can see here steam is coming, so this is a steam turbine which on expansion produces electric power, and here the gas is coming, that is syngas, so this is a gas turbine. Coming on to one another uh, numerical question. Just a second. Okay, let me start with this question, which is a low grade coal is combusted in a fixed bed reactor. The uh, the composition of flue gas, that is dry bases emitting from it, is as follows. On dry bases it is given, so it has given 15% CO2, 5% O2 and the rest is nitrogen, that is inert, basically air we are considering. So from these data calculate the percentage carbon and hydrogen in the dry coal. So let us start with this. So here initially what is given, it is given that 15% CO2 and 5% O2. So let us consider that if we take, let us assume we have taken 100 moles of low grade coal. So we can say that 15 moles of CO2 is there and 5 moles of O2. So after that the rest is N2, which is 80%, that is 80 moles, which is 100 minus 15 minus 5. So let us take that X moles of air are supplied. So as we know that 79% of nitrogen is there in X, so if we do 79% of this X mole, it is 80, this 80, okay. So we will be getting the moles of air supplied, which is 101.265 moles. Let me calculate. The reactions taking place, basically the combustion reactions that are taking place, are basically formation of CO2 and formation of H2O. Okay. So let us see the amount of oxygen supplied. So this is the moles of air supplied. These are the moles of air supplied. These are the moles of nitrogen supplied. So the moles of oxygen supplied can be done by the moles of air supplied into 0.21, which is 21.265 moles. This is the amount of O2 supplied, but the O2 used in combustion, it is given here that we have got 5% oxygen after combustion. That is the flue gas emitted. Flue gas after the combustion consists of 5 moles of oxygen. So the moles used can be written as, so basically these 5 moles are excess moles. So these are the supplied moles. So supplied minus excess can give the moles used. So it is 16.265 moles of oxygen are basically used in the combustion. The amount of carbon present in dry coal, it is 15 moles. Since after combustion it gave 15 moles, so that is the amount of carbon present in coal. So in as we can see that in carbon dioxide, if 15 moles of carbon are consumed, then 15 moles of oxygen are consumed. So the remaining moles of oxygen after consumption, here we can see that if 15 moles of carbon are consumed, that similarly 15 moles of oxygen are consumed. So after this reaction, the after consumption of oxygen in this reaction, these many moles of oxygen are still left for consumption. As we know that the total oxygen moles consumed are 16.265, 15 moles are consumed in this reaction of oxygen. So the moles that are left for consumption in this reaction are these. So if 1.265 moles are consumed of oxygen in this reaction, so how many moles of hydrogen are consumed? Basically it is twice of oxygen. So now let us calculate the weight of carbon and hydrogen in dry coal. These are the moles of carbon in dry coal. So the weight will be 15 into its molecular weight, which is 12. It will be giving 180 grams. Now weight of, okay, let me take another slide. Okay, let me write here. So the weight after this, it is here, weight of hydrogen in dry coal, it will be 2.53 into 2, that is the molecular weight of H2, which will give 5.06 grams. So what we have to calculate in the question, that is the percentage of carbon and hydrogen in dry coal. So the percentage of carbon, it will be 180 upon the total concentration of dry coal, that is 180 plus 5.06, which will be giving us, okay, percentage we have to calculate, so it will be 2.73 percentage of, sorry, this is, it is 97.26 percentage, and the percentage of hydrogen, it will be 5.06 upon 185.06 into 100, which will be giving 2.73 percentage. So the answer to this is carbon percentage is 97.26% and hydrogen percentage is 2.73 percentage. This is the last portion. Okay, then coming to the next question, that is calculate the amount of work done in the burning of coal in a nickel based chemical loop combustor, but when the change in entropy is 420 joule per Kelvin and working temperature is 400 Kelvin. These are the equations given. Equations for the combustion are given here. So this question is quite similar to the last one. This is the oxidation of nickel to nickel oxide, which is an exothermic reaction, and this is the reduction of nickel oxide to nickel, which is an endothermic reaction. So this is Q hot, this is Q cold. Q naught will be calculated using T delta S, which is 420 into 400 Kelvin, and we will be calculating W from here. So let me do, it will be simply W equal to Q hot, which is 396 minus 136, which is Q cold, minus 400 into 420 upon 1000, because both these are in kilojoule. So we will convert this in kilojoule. So after this we will be getting the answer as 92 kilojoule. Coming on to the next question. In a fixed bed gasifier, air flow rate and feed flow rate are 25 normal meter cube per second and 12 kg per second respectively. The feed material does not contain any sulfur, nitrogen and chloride. The syngas contains carbon monoxide 45%, carbon dioxide 2%, hydrogen 25%, methane 5%, C2H2 2%. So calculate the rate of production of syngas in normal meter cube per kg of feedstock. So the formula for this question I have shown in the slides. So the formula for the rate of production of syngas is air flow rate into 0.79, we will be doing nitrogen balance, upon 1 minus CO minus CO2 minus H2 minus CH4 minus C2H2 upon 100 into feeding rate. So after putting all the values in the question, that is air flow rate is 25 normal meter cube per second, which is 25. So 1 minus carbon monoxide is 45, carbon dioxide is 2, hydrogen is 25, CH4 is 5, C2H2 is 2 upon 100. And feeding rate is 12 kg per second. So after solving this 100 will go here, and after solving this, we will be getting 7.84 normal meter cube per kg of feedstock. Coming on to the next question, the shift conversion reaction taking place during water gas manufacturing is given by. As I told, that water shift reaction is the reaction of carbon monoxide with steam or H2O to give carbon dioxide and hydrogen. So the answer is third one, that is CO plus H2O gives carbon dioxide and hydrogen. Which of the following is not the benefit of direct liquefaction of coal? The answer is high capital cost. Just a second. Are the questions clear to you? Okay, let me move forward to the last question of the session. The question says a low grade coal is combusted in a fixed bed reactor. The composition of flue gas, dry bases emitting from it in as follows, that is 15% CO2, 4.1 oxygen, and the rest is nitrogen. From these data, calculate the percentage access air used in this process. So it is given that low grade coal is combusted. So the composition of flue gas on dry basis is given, which consists of these uh, components. So let us start the question. Firstly, so assuming 100 moles of flue gas, so it will be 15.3 moles of CO2, 4.1 moles, and nitrogen will be 100 minus 15.3 minus 4.1, which will be giving us 80.6. So oxygen supplied in air. So let us assume X moles of air. So nitrogen is X into 0.79. So we will be getting 102.02 moles of air. So oxygen in the supplied air will be 0.21 of 102.02, which is 21.42 moles. Now oxygen consumed in combustion, these are the oxygen supplied with air, and this is the question. In the question it is given which is the excess oxygen as it is given out with flue gas. So the consumed will be given minus excess, which is 17.32. So minus 4.1, 17.32. Okay, so this is 17.32 moles. So percentage excess will be excess moles present upon moles consumed, which is 17.32. It will be giving us 23.67 percentage of excess air. So the answer is 23.67 percentage of excess air. Okay, then we have time, so I can introduce one more question. Question 3 and 4. Okay, so question 3 and 4 you want to see. Just a second. Okay. Which question 3 and 4 actually there is an assignment and some additional questions. So which question 3 and 4 you want? The assignment or additional
Yeah, this
questions?
one only.
Hello? Could you please answer the additional questions or the assignment
The
part?
assignment one.
Okay, okay, just a second. 3 and 4, okay. By the way, for your information, this PPT will be uploaded. Mean the link to the drive will be provided to you, so you can access all these questions and slides later for your preparation purpose later also. So there is you can also watch this video on YouTube for later purpose if you want. So both the link for the recording as well as the PPT will be provided to you. Okay, then let us come to this question. It is a bit lengthier, so we have time we can do. So just give me a minute. Okay, now coming to this question which says, let us assume the gasification reaction. This is a gasification reaction which is given. 100-gram each sample is given, which has a formula. It is given here. If the above material is gasified in a fluidized bed gasifier, what will be the composition of syngas when peat to oxygen ratio is maintained as 0.7, that is mass to mass ratio, and steam to peat ratio is also maintained as 0.2, that is again mass to mass ratio. Assume carbon monoxide to hydrogen ratio in syngas as 2:1, that is volume to volume. Ignore the presence of other impurities and consider the molecular weight of the ash as 56. Also calculate the yield of hydrogen and carbon monoxide. So, this is the reaction given. The mass is given as 100 grams. So, using this reaction and this formula, we will be doing the balance. Firstly, we will be doing carbon balance. It will be giving A equal to H plus J. Since 1 mole is A here and this H and J. Then coming to, just a second. Hydrogen balance, which will give B plus 2F, F and this 2, plus, sorry, 2I plus 2M, as here 2I and 2M. Then further oxygen balance C plus F plus 2G gives 2H plus J plus 2K plus M. Now coming to nitrogen balance, which is D equal to 0.03, just a second, 0.345. Sulfur balance E equal to K, and which is given as 0.0043. Ash balance is not required. Okay, then moving forward, what is given in the question, that is mass of peat upon mass of oxygen ratio is given 0.7. So mass of peat is given in the question. So with this we can find out mass of oxygen, which will be 100 by zero point 0.7. So it will be 142.85 grams of oxygen. Another thing is, okay, so with this we can also calculate moles of oxygen. One 142.85 upon 32, that is O2, which is 16 plus 60. So it will be giving us 4.464 moles of O2. So these are the moles of O2 used per moles of peat. So it is basically G value. This one. Moles of O2 used per moles of peat used. So this is G here in this equation. So one variable we have got, which is G equals to 4.464. Another is mass of H2O upon mass of peat ratio is given in the question, which is 0.2. So mass of H2O can be calculated, which is 100 into 0.2, which will be giving us 20 grams. So moles of H2O, which will be 20 upon 18, which will be giving us 1.111 moles, which is the value of F. This here, this value of F, the mass of moles of hydrogen used per moles of peat. Also, there is one more thing in the question given, which is CO ratio H2 is given 2:1. According to that, by that we can find that J is equal to 2I. Okay, it is given here. CO ratio H2 is 2:1. So CO is J and H2 is, sorry, I. So ratio of J to I is 2. So with that we can get J equals to 2I. So going further, coming to the H balance equation, 2I plus M equals to 10.088 plus 2 into here value of F is substituted. With this we get I plus M equals to 6.155. So let us take this equation as A. Now coming to O balance equation, substituting the value of G and F, we get H plus 2I equals to 4.228, and taking this equation as B, substituting here J equals to 2I, we get this equation. So these are the four equations. This equation, this D equation we got by doing C minus B. By doing C minus B, we get this equation. Then by doing D minus A, we get H minus I equal to 1.8274. Then doing 2 into E plus equation B. Now going forward, let us put value of H in equation B, and J equals to 2I, which is given in the question. It is 1.6004. Put I in equation A and we will get M equal to 5.3548. So now let us come. We have got all the variables. Now let us write down the composition of syngas. Composition of our syngas, which is CO2, which is A, A, which is the addition, just a second, addition of H plus J. So total moles after adding all of them will be 10.4218. We have calculated this CO, suppose CO2, I have taken the moles of CO2, just a second, let me tell you. This H is the moles of CO2, so the H value we got as 2.622, so the moles of CO2 will be H. So likewise, I have done here H, then for CO I have taken J, for H2O it is taken M, SO2 it is taken K, and N2 D. So the total moles we have done by adding all these. So now composition of syngas in volume. So it will be done for C, it will be 2.6276 upon 10.4218 into 100. So likewise we will be getting all the compositions: 25.212 percentage, 15.3562 percentage, 7.67 percentage, 0.0412 percentage, 0.331 percentage, 51.38 percentage. So what is asked in the question? Hydrogen yield. It is basically the H atoms in syngas upon H atoms injected in sample or during the reaction. So in syngas, H atoms is 2I, as it is shown, it is 2I, and supplied is 10.08. This is the formula of feed, so this is the supplied hydrogen. And C atoms injected is 4.228, and for CO yield it is J. In syngas amount of carbon monoxide is J. So it will be 2I upon 10.088, which will be 0.1586 is the yield. And CO yield, C atoms in syngas upon C atoms injected. It is 1.6004, which is J value, upon 4.228, which is given in the formula. So the answer is 0.3785. So this is the question done. So this was the last question for the day. Is this clear to you? Am I audible to you guys? Some kind of confusion if you have some questions?
Can you show the second page of the last question?
Okay, just a second. Second, there are 3 pages. The second one you want, right?
Yes,
Yeah,
this one only now.
yeah. I know it is a
Okay,
lengthy
thanks.
question. It is a bit confusing, but if you guys practice, it will be fine. I mean, it is not that hard. If you guys practice, it will be getting more handy to you. Is it done?
Yeah, okay.
Okay. So, if there are no questions, then we can end today's session. Okay, then that's it for today. You guys may leave the class.